In hydraulic clutch control, the pedal acts on a master cylinder connected by a hydraulic pipe and flexible hose to a slave cylinder mounted on the clutch housing. The slave cylinder operates the clutch release fork. This vehicle uses a center valve master cylinder. With the pedal in the off position, the center valve is clear of the inlet port and fluid can flow to or from the reservoir into the cylinder. When the pedal is initially depressed, the piston is moved forward, taking the valve assembly with it. The center valve closes off the inlet port from the reservoir, trapping fluid in the cylinder bore. Further piston movement displaces fluid through the outlet port and into the connecting lines to act on the slave cylinder piston. The movement of the slave cylinder piston is transferred through a push rod to the clutch release fork to operate the clutch. When the pedal is released, displaced fluid returns to the master cylinder and the center valve returns to being slightly clear of the inlet port. In light vehicle applications, the pressure plate is normally a diaphragm type and is serviced as an assembly. It consists of a pressed steel cover, a pressure plate with a machined flat surface, a number of spring steel drive straps, and the diaphragm spring. This diaphragm is located inside the clutch cover on two fulcrum rings, held by a number of rivets passing through the diaphragm. The pressure plate is connected to the cover by the spring steel drive straps, riveted to the cover at one end and to projecting lugs on the plate at the other. Retraction clips hold the pressure plate in contact with the outer edge of the diaphragm. During clutch operation, they move the plate away from the flywheel. This section examines the driven center plate, also called a clutch disc or friction disc. The driven plate has a pair of friction facings, usually of wire-reinforced asbestos composition, carried on wavy spring steel segments, which are riveted to a steel disc. The central alloy steel splined hub is separate. Drive is transmitted from the disc to the hub through heavy torsional coil springs or rubber blocks. This spring hub arrangement dampens torsional vibrations from the engine. It also absorbs shock loads imposed on the driveline by sudden or violent clutch engagement. Stops limit the radial movement of the hub against the spring force. A molded friction washer between the hub and spring retaining plate also acts as a dampener. The waved spring steel segments cause the facings to spread slightly when the clutch is disengaged, then compress as it is engaged. This has a cushioning effect and provides smooth engagement. This section examines the throwout or release bearing. The clutch release bearing can be a thrust-type angular contact ball bearing supported on a carrier. It slides on a hub or sleeve extending from the front of the transmission. The bearing carrier locates on the clutch release fork. Moving the fork brings the bearing thrust face into contact with the pressure plate fingers. This causes the bearing to rotate and absorb the rotary motion of the fingers against the linear motion of the fork. The bearing is packed with lubricant during manufacture and requires no periodic maintenance during its service life. In light vehicle applications, the engine operates over a wide speed range, but produces maximum torque only within a relatively narrow RPM band. A relatively large turning effort must be applied to the driving road wheels to move the vehicle. Then the turning effort must vary to overcome air and gradient resistance and rolling resistance. A manual transmission allows the driver to directly vary the gear ratio between the engine and the driving road wheels. This allows engine torque to be varied to suit load and speed requirements. The transmission also provides a means of reversing the vehicle. And it has a neutral position, which disconnects the engine from the driving wheels. When two gears are in mesh, one is a driven or output gear. The other, providing the turning action, is the driver or input gear. A gear ratio is the number of turns of the input gear necessary to achieve one turn of the output gear. Here it is 1:1, since the gears have the same number of teeth. In rotation, they also turn at the same speed, and the turning effort of the output gear will equal the effort applied by the input gear. The gear ratio can also be calculated by dividing the number of teeth on the driven gear by the number of teeth on the driver gear. In this case, the driven gear has 30 teeth and the driver gear has 10. So the ratio is 3:1. The driver gear has to turn 3 times to turn the driven gear once. In continuous rotation, the driven gear turns 3 times slower than the driver. Lower speed produces higher torque. So torque at the output is higher. For this gear ratio of 3:1, if input torque is 100 Newton meters, then output torque is 3 times that, 300 Newton meters. When 3 gears are in mesh, the input and output gears are meshed with an idler or intermediate gear. The idler transfers movement between the input and output gears, but has no effect on the ratio or the torque multiplication. These remain unchanged. Compound gear trains have 2 or more pairs of gears in mesh so that they rotate together. This compound gear train has gears on 3 shafts. The gear on the input shaft meshes with a larger gear on a countershaft or cluster gear. The countershaft has a smaller gear formed on it, in mesh with the output shaft gear. The motion of the input is transferred through the large gear, along the countershaft to the smaller gear, to the output. The output turns in the same direction as the input, but at a reduced ratio, depending on the relative sizes of the gears. Since 2 pairs of gears are involved, their ratios are compounded or multiplied together. The input gear with 12 teeth drives its mating gear on the countershaft, which has 24 teeth. This is a ratio of 2:1. This ratio of driven over driver at the input, 2:1, is then multiplied by the output ratio, which has a driven to driver ratio of 3:1.